Let's get started. All right. So, where did we leave off last time? So last time we were talking about how to compare the behaviors of programs, tell when they're equal, and more than just simply running them, which is pretty boring, but like, can we apply reduction rules in other contexts and kind of treat this like an algebra class? But there are problems. So I had a notion of, people go by different terms, contextual equivalence or observational equivalence, which says that two programs are equivalent when they give the same result when embedded in the same context, for any context you could possibly pick. And that is useful for deriving a number of equalities. But here's a couple of annoying ones, right? So the first one is, right, I've got normal. I had my functions in Boolean, so not and, boring definitions. Not of x, right? The function which turns x into not of x is not the same thing as the identity function. Or is it? Morally, it should be, but why not? Right? What's the difference? Can anyone remember? Yeah, I could plug some random weird non-Boolean into it. So I could plug in, for example, I could apply these functions in the context like this, lambda y dot true. It's just an example of a not Boolean thing, right? So when we plug the right-hand side into the box of this context, it's fine. I just get the same lambda back. When we put it in here, it will get stuck. Because if then else doesn't make sense on lambdas, I haven't said what that does, right? Same thing here. I just get stuck in certain contexts, right? And so what are those? And so what's the reason? So why aren't these the same? Right? We kind of want to say, well, x and y should just stand for true and false. But if all I say is, we'll plug it into context that might be something of the shape, let x be v1, y be v2 in box, right? So this is a closing context. I'm giving meaning to the free variables by substituting in values, right? We can also make this get stuck, which is not really interesting, right? I'm not actually interested in these contexts. I want to say, fine, yes, syntactically you can write this, but I don't care. I don't want to count this as a counterexample because you shouldn't be writing programs like that anyway. And same thing here. These should ultimately only be Booleans, right? So these should be either true or false, right? If they're values, I don't want you plugging in lambdas, or if I have numbers, don't plug in numbers here because they're not numbers. God forbid we confuse numbers with Booleans, right? Who would ever do such a thing? So that's where I'm going to start. In just like maybe not yesterday, maybe the day before, where I started with this kind of gold standard of what does it mean for programs to be equivalent, and then how do we come up with a tractable syntactic approximation of that? I'm going to do the same thing today. What is a typed notion of equivalence, where I'm going to rule out certain context based on typing information so that we don't have to worry about these annoying counterexamples that no one cares about, right? So that's going to be the start. So let's start with a notion of typed. There we go. Defin of typed observational or contextual, depending on contextual, depending on who you ask, equivalence. Right? And this will be a little bit easier than last time because types are going to do more than just rule these things out. We're going to get some other properties for free, which means we get a slightly simpler definition in certain parts. So it's going to look like this. So we're going to have two terms, m and n. And I want to say, when are they equal? And in order to tell if they're similar, or when are they equivalent, I need to know what type they have, right? So the types, in a sense, you can think of this as the types telling me the two programs are equal because they tell me how I'm supposed to compare the types. What is the valid observations that I can make on the types. And these terms, just like and well, especially and, this is a closed term, so that's fine. But these are open terms. So if you have free variables, you should also tell me what is the range of significance of these free variables. Like, what are you allowed to plug in for them? Otherwise, we'll get stuck again. So we also, just like in type checking, I need an assignment for free variables. So this is my relation that I'm setting up. Just to make it clear, this is going to be a sort of semantic relationship, so it's not inductively defined by some rules, but still is a relationship between a typing environment, two terms, and a type, right? And when are two terms equivalent at a type? There's slight variations on what you can do here. I'll try to stick with a fairly standard and simple one. So what's the first thing that might make sense to say? So if I say m and n are equivalent at a type, I might want to say they have that type. That's a reasonable assertion to make. So that means that m needs to have type A and n needs to have type A. I can make that stipulation, but certainly that's not enough. So what else do I have to do? What's kind of the name of the game? Yeah, for all contexts, right? And Amal was, so I'm doing something slightly different from Amal, but we will get to logical relations soon, and you'll have that. So I'm going to do these kinds of contexts, so things that surround a term. But it should, I only want to consider the ones that make sense in terms of the types, yeah. Yes, so you want something about types, and a lot of people do typed holes. I want more than evaluation context, though, because I want to say this applies in arbitrary contexts. So I'm doing arbitrary contexts. That's a slight difference. And I'll say for all contexts. And I could spend a long time setting up a bunch of rules, saying when do I have a context with a hole expecting type A and then producing a result of some other type B. And oh, by the way, the context might capture some variables. And so I'm going to have to you can do this. You can spell out all the rules. I'm going to cheat because we don't have time. I'm just going to say kind of from the outset such that, what is this? Well, I'm going to say that it's going to be a closing context. So when I plug in the term m into C, closing context means there's no more any free variables. So I'm going to type check this. I'm going to say it has no free variables. So that's empty. And what type should it be? There's a few options you're going to make. I'm going to be fairly conservative and say, well, what programs do I know I definitely can run? And it can definitely be sketchy to say I run a program at a function type and get some weird closure at the end. It's like saying, well, I ran my program for a while, and then I have a pointer to the closure on the heap, and I'm going to inject the pointer into this free code that I don't know what you're doing with. So let's just play it safe and say the program should return a Boolean. Certainly, if a program returns a Boolean, I know how to deal with that. It's going to be true or false stored somewhere in memory. So it's not too spooky. So we have this. So we have C closes over M, and C closes over the other term N, and gives me a bool. So I kind of know from the outside, at least, that this context makes sense with the typing rules I already have. And what else do we want to say? Well, we had something before that, if M reaches a value, then N reaches a similar value, and vice versa. I'm just going to kind of say this all right. So I'll say that implies that if the total program, M plugged into C, if that reaches a value, then W reaches a similar value, and this is the operational semantics. All right? And what is my similarity relationship for bools? All right? So when are two Booleans similar? All right, so true is equivalent to true. And false is a similar value to false in terms of bools. And are there any other bools to consider? Nope. Do I have to worry about weird, awkward situations where I have lambdas with random code inside and it's hard to really judge what's in the code? Nope, those aren't Booleans. This is why I'm limiting myself to Booleans. It gets rid of all of these weird existential questions. We're just going to limit ourselves to running Booleans and comparing Booleans, which should be fine in some sense. Everything you want to know, essentially, if you want to ask a question about a term, you can sort of write a program as some context that takes that term and tests it somehow and then returns true or false, depending on if that property is true. Right? That's the idea. Right? I have two different outcomes that I could have. Yeah?
Does the last line say if Cn reduces, or it says?
They both have to reduce. So what I'll get at the end, if any two things are contextually equivalent, I will automatically know two things. One, I'll know that it terminates. And two, I'll know that it's type safe. Right? So I'm automatically getting some other kind of important properties just as corollaries from this sort of thing of contextual equivalence that I can't really do in the untyped setting because A, in an untyped setting, I can have type errors, and B, things might not terminate. So the idea here is with typing rules, I'll have that property, and it lets me simplify things. I could be cautious, and it won't give me anything.
Yeah. Would any atomic type work, or is...
Yeah, if I had like ints, that would also be fine. But also, it doesn't really matter, because if I also had ints, I could say anything you'd want to know about ints, concoct a test, and then say true or false.
So the unit type, does that also work?
Unit type technically works and is boring, because there's only one value. So I can never say two things are different. I want at least two different results, so I can say two programs are not the same. Right? So I want something that is inhabited by at least two things. Right? That's an important thing. Other than that, I don't care. You can generalize to all ground types. There's like a lot of things you could do. I'm just keeping things simple. It's enough, right, to just have two outcomes. Yeah.
So sorry, could you repeat the atomic?
Could I have other ground types was the question. Yes, I'm not going to do it here. Yeah.
If you have other ground types, then are these notions of equivalence equivalent?
Yes, that's kind of what I'm getting to. You could do it at all ground types. So if you have other ground types, you can say at all the ground types, you can say at this one. I don't want to dwell on this too much. This is just my definition, and we're going to roll with it. I'm sure we can ask questions all day about many of these things. I do want to kind of get moving to the next topics a little bit. So let me get going. So this is my notion of semantically what it means based on the behavior of how I run programs. And now, well, I want to tell you some rewriting rules that I will claim works, and then say, how do I prove that those actually work according to that definition, which is something that I care about, and hopefully you care about too, that if two things are equal, they're equal in all contexts. So let's look at what those extra principles are. And, well, based on here, let me do it over here. Let's start with Boolean, because I think that might be the slightly easier one based on our examples. So what's missing to stop me from finishing these proofs and saying that they're equal? Like, how would you do this mathematically? How would you say that not x is equal to x? Yeah. Case split, right? What could it be? True. It could be false. Either way, it works out. So I want a syntactic kind of rule that lets me do a case split based on an unknown Boolean, right? If you give me a Boolean, well, I don't know what it is, but it must be either true or false. That's the idea. And there's different ways to write it. And again, I don't want to dwell too much on the thousands of different design decisions we could have. If you have the questions, we can address those afterwards, right? But I will write this rule in two different ways, right? And so the first, I'm going to write it as, well, I guess before I do that, I need to, no, I'll write these rules, and then I'll kind of do the rest of the equational theory. So just like here, I have a judgment or a relation between a typing environment, two terms, and a type, which has a semantic meaning. I'm going to do another one, which is just going to be inference rules. So it's purely syntactic. It's just based on rewriting the shape of terms and nothing more. OK, and that is going to look like this. I'm going to have the relationship, I'll write it over here, is going to look like this. I'm going to also have a typing context, and I'm just going to say m is equal to n at some type A. So straight bars mean syntactic inference rules, just over the structure of terms, and the squiggly bars mean how the things run. That's the difference in notation. How we can tell these two relationships apart. I mean, we're going to want to prove that this one implies that one. That's going to be the ultimate goal. Okay, so the case split on Booleans looks like this. So if, I'm going to write it this particular way, if I have, I think this is the way I have it in the notes, m is equal to n. So how do I judge? So I'm filling in, I'm using an m and n. And m and n are going to be arbitrary equal Booleans. I don't necessarily know what they are. They might be a free variable, right? So how do I know that m and n appear equivalent? I'm just doing evaluation context for here, is doing the case split. I need to prove that these two contexts will do the same thing if I plug in true and if I plug in false, right? That's the case split. That I don't know necessarily what m and n are, but I know they're equal. And I know the rest of my program continues the same if I specifically plug in trues and falses. So that looks like this. I'll have a proof that E, and this should be, well, let me do E prime. These are two different contexts. So E is equal to E prime when we plug in true. E prime when we plug in true. Some type A. That's one premise. And then my other premise is that E is equal to E prime when we plug in false. Okay, of type A. And if we're going to invent names for these rules, sometimes this is a rule for Boolean, right? It's not an introduction rule or an elimination rule. Sometimes I call it X for extensionality, not to confuse with another version afterwards. So this is sort of an extensionality principle for Booleans in the sense that, or you could also think of an induction principle, right? Two Booleans are only equal if they are in a context, right? If I can plug in true and false, right? So if I know that they're equal, I can do that and continue on. And so, for example, here, and is morally speaking an evaluation context on X. So I get to arbitrarily pick true or false here and say, well, if I plug in true, I get the same answer. If I plug in false, I get the same answer. Yeah?
Why is there equals n? There m equals n if they're bool and n equals n.
Just to make your life easier, right? I could put the same m in, I guess. But like I said, I won't dwell too much. The main question and the main ultimate thing is I can write down anything I want as long as it's sound with respect to that definition. This is the one that matters. The syntactic rules don't matter so much as long as you can prove useful things. So I don't want to dwell on design decisions, right? Yeah.
Maybe the question was, why do we say that m equals to n both in type bool and in type A?
So these are two bools.
Yes.
I'm plugging it into an evaluation context. I have two different evaluation contexts in two different terms. How do I know that the overall combinations are the same? Well, I have to check that they're the same Boolean. And then over here, I need to say, well, for the rest of the program, right, so this is a choke point.
Oh, okay.
So the Booleans are going to have to either both return true or false. That's what's going to be this first premise. And then from there, if I plug in true into both evaluation contexts, I do the same thing. And if I plug in false into both evaluation contexts, I do the same thing.
So do we have three premises in the rule?
Yeah, three premises.
Okay.
Yeah, this is a rule of three premises. Right? So I need to know that I have the same bools, and I need to know that my evaluation context will continue to do the same thing as long as I plug in the same actual Boolean values on both sides. Okay? So this is the one rule. And then there's another type of thing that I have, right, which is functions. And does anyone know what kind of this extensional reasoning principle for functions looks like? Has anyone heard of something before? Yeah. Either one.
Function extensionality. Like
Yeah.
you evaluate functions that return the same value
Yeah, functions are the same when they return the same result on the same input, right? This one's a little bit trickier to phrase. You might think this one's weirder. This one's slightly trickier to phrase, so I kind of started with Booleans first. So what does function extensionality look like? So let me actually start at the bottom. So two functions, m and n, are equal at type A arrow B when, for all possible inputs I could plug in, they're equal inputs, and I get equal outputs. So if I'm going to write a syntactic rule, it's kind of hard to have infinite numbers of premises, right? That wouldn't really be a good syntactic rule. So here's a hack that you can use to do it. I'm going to say, well, if I plug some x into m and some x into n, they're equal, where x is some arbitrary unknown a, then I better get an equal b, right? So the idea here is I don't know anything about my input x other than it has type A. That's my only information. So when I substitute something in for x, by kind of iterating through all the possibilities it might be infinitely many possibilities, I generate all of the infinitely many premises, right? Because if it's just Boolean, then I can plug in true and false. If it's a function type, like bool, arrow, bool, then I have allowance to plug in every possible function of type bool, arrow, bool, or some other type. Yeah.
Why doesn't it have a relation context or some condition that those have to be closed?
Well, we're dealing with open terms, first of all. I will need the fact that these are evaluation contexts at some point. There's a reason for that. We haven't gotten there yet, though, so we'll have to hold our horses. Yeah.
So your rules are using like the equal sign, not
Mhm.
necessarily equals. And like I would expect not x and identity x to be extensionally equal, but they're not syntactically equal, so I don't see how it would fit your rule.
So how they fit the rule. So up here, not x.
You need to evaluate down to like a Boolean.
So I'm going to have some more rules. Let me write down some of those now. So this isn't all of my rules. So I've got a bunch more rules. And let's start writing some of them down. So what's one of them? So I'm going to have, so what else should equality have? So I'm defining this inductively, so I need to add all the properties that I need, right? Oh, it's escaping slowly. Hopefully you wrote it down. I'll bring it down. So what else do I need? So what are some obvious properties that if this is an equality relationship, what do I have? I think I heard reflexivity. That's like an obvious thing. So, you know, what is this? M is equal to m. And I need a type. So at type A. So are all terms equal to themselves at type A? So is true equal to true or at type bool, arrow, bool? That's OK. So maybe the term should have type A. This is kind of a partial equality. As long as it's a term of the type, then I have reflexivity, right? So refl looks like this. If m is indeed a term of type A, then it's equal to itself at type A. That's an obvious property I should have. What's another one? I should have symmetry, right? These are just the things that we know how equality is supposed to behave. So if I know that m is equal to n at type A, then n should be equal to m, also at type A. This is symmetry. OK. What are some other properties? Transitivity, right? So if I have a pair of equalities, I can stick them together. So if I have that m is equal to m prime at type A, and m prime is equal to m double prime at type A, then m is equal to m double prime at type A. Right, so this is transitivity. Okay. And then there's one more really important rule that we normally look over and mathematicians don't really bother with.
Injectivity.
What was that?
Injectivity.
Injectivity. So what do we mean by injectivity? That might be what I'm thinking of.
Same function applied to same stuff.
Same function applied to same stuff. That's kind of that one. This is my extensionality rule for functions, but it's very closely related. So rather than function with contexts, if two things are equal, then they're equal in all contexts. right? Now, I called it compatibility before. Some people call this congruence. And if you model context as functions, then it's like injectivity, right? These are kind of the same ideas. That equal things are equal no matter how you use them. This is probably the trickiest one to write down. I want to make sure I get it right. And it's because this thing, while very useful to use, or compatibility, yeah, this one is very easy to use, but really hard to justify. So we're not going to justify it directly. So this one looks like this. So if I have two equal things, so if m is equal to n at type A, then I should be able to stick them into arbitrary contexts, right? So it's the same context. Then I can stick that in. But the context better be well typed with respect to these terms, right? So that means if I plug in m into the context, I get back some b. Like I said, I'm avoiding giving typing rules for context. It's very tedious. So plugging in m into the context gives me a b. And c might capture some of the free variables of m. And it might have some of its own free variables. So this is some different gamma. All right. And then if I do the same thing, plug in the other side n into the context, I also get something of type B. Then I kind of ran out of room there, but that's fine. So then what else? So if they're equal and I plug them into the same context, then that should be equal, right? At that other type. So that means at gamma prime, C of m should be equal to C of n type B. Okay, yeah.
Is it possible to write a similar but related rule where you can introduce these variables into a context and you kind of move all of that down to the bottom?
Yes. Yes, there's a different way. So I'm eventually going to eliminate compatibility, or at least describe how you do it. I don't have time to actually do it on the board. But you don't want to prove properties about this rule because it's really painful. Yeah.
Sorry, just if you could repeat the question.
Yeah, so can we start from the leaves and kind of push it down? And that's exactly what I'm going to do. One more question. Yeah.
Do you need gamma contain a gamma prime?
I don't know. Maybe. Probably not. I don't personally care. I'm not really going to actually prove so do we need gamma contain a gamma prime? I'm just going to syntactically deal with this rule, right? So doesn't matter. There's one other rule that's super important, probably the most important rule, honestly, which is we already have an operational semantics, right? So if I take a step, then the thing I step to ought to be equal to what I started from. There's one more rule that, let's see if I can sneak it in here. So it's my stepping rule that if, and I'll write it like this, if, well, let me put it over here just so it's not too confusing. If m takes a step to m prime, and there's different ways you could write this. So what do I need to know? I need to know that I start at some well-typed m, and then I take a step, and I need to land somewhere well-typed, right? Technically, I probably proved preservation, which is what this is useful for, but you can also just add it as a premise. I'll kind of sneak it in this way, sort of like mixing in with transitivity. If m prime is equal to n at type A, that means that m prime also has type A. So I start at type A, I take a step, and I end up at something at type A, and it's equal to an n. Then that is equal to, not equal to, but that it entails that m is equal to n at type A. So I take one step into an equality, and I fold that into the equality. So this lets me, all those beta rules I had before count as equalities. These count as equalities. All right. So there's other ways to phrase this. You may have heard other things for extensionality of lambda calculus, for example, the eta rule. All right, so lambda calculus gives us three important laws. Alpha, I very quickly talked about, that was going to be lecture 1. Beta, which is how we run programs, and eta captures extensionality, which is equivalent to function extensionality. So these are in the notes if you want to do some practice. Some of them are just purely syntactic and I think are really fun. Others are harder semantic stuff. So the eta law for functions is what? If I have a function defined as taking an input and then just passing it to m, if I never use that x again, then it's the same thing as m, right? I haven't changed anything. So this is equal to m. And then there's two caveats that I need. So does anyone know the side conditions that stop this from being horribly broken? Yes, so m doesn't talk about x, which you're right is saying it has no free variables x, or x is not in its set of free variables. So we need the side condition that x is not in the set of free variables for m. And one more, make sure it's not ridiculous. So this rule tells me that true, which doesn't have any free variables x in it, is equal to lambda x true applied to x. Clearly bogus, so this should be something of type A arrow B. All right, so that's the other caveat we need. So this is the one for functions that hopefully everyone has heard about one way or the other. Maybe you're fighting with linters for functional programs and it says you should eta reduce here, and that's what it's talking about. What about the one for bool? So this is like a fun game you can play. Rather than inference rules, I can capture these in axioms. So these are just axioms. I'm saying they're true, period. As long as m is a term of type A arrow B, and I can pick some fresh variable x that m's not already using, I can do this expansion. How do we do that for bools? Has anyone seen this one before? This one's a lot more rare. But we can do something like this. Suppose I have an if-then-else where I'm checking m. And if it's true, then I plug true into the evaluation context E. And if it's false, I plug false into an evaluation context E. Is that then the same thing as saying E with m directly? Doesn't really matter what the type is. So what am I saying? Run m. If it's true, I plug true into the evaluation context. If it's false, I plug false into the evaluation context. And that's the same thing as just running m and then passing it directly into the evaluation context, assuming it's a Boolean, because that's the only things it could return, right? So that's an eta rule for bool. And you can prove with compatibility that these two presentations are exactly the same. You can derive these inference rules using those axioms. You can derive those axioms using those inference rules without really knowing anything about semantics. You're just pushing symbols around. Okay? All right, I just kind of want to mention that because I know most people here have heard of at least eta for functions. I want to mention you have eta for other types of things too. It doesn't look like eta for functions, of course, but it is a little bit different. All right, now I want to start working on my proof that this equational theory, which is now done, I'm leaning heavily on the operational semantics, of course. I added a few more rules for doing things like case splits and function extensionality. But other than that, we said, well, it's transitive, reflexive, transitive, reflexive, symmetric, and compatible closure of the operational semantics and these extensionality principles, these reasoning principles. These are just some syntactic rules we can do. So now the goal is, how do I know that arbitrarily rewriting terms in this way means something about how programs run, right? And the rewriting theory that we did before is going to struggle with this kind of thing, especially with all of these weird extensionality principles in particular. If we just stuck with the operational steps, it's no problem. But it's doing stuff like case split that becomes hard to show. So the answer is, well, we've already seen what's going on is all of Amal's lectures on logical relations, right? They were talking about unary predicates, she mentioned, things like safety, termination, stuff like that. But we can generalize that to binary predicates, which is, are these two programs equivalent, according to this notion of equivalence? and then build this logical relation where essentially the idea is for every type in my programming language, I come up with a different relationship between terms, right, which sort of somehow reflects the meaningful context that I can use them in or their behavior and how they run, right? So let's get started doing that. I know Amal's already given lots and lots of lectures about kind of how they're set up, why they work, so I won't dwell on that part. But I'm going to show a binary logical relation for proving program equivalence. I'm going to do it with a very different style, some of which is notational and stylistic, some of which is different. I don't want to, so if you have questions about why do I do it different than Amal, I want to address them after the lecture. Otherwise, we'll take forever. Just put that out there. So I'm going to define, and really, the requirement to be a logical relation is it's a relation on terms defined for every type. That's what it is. That's the logical part. The logic is every type, and it's a relation. And this is going to now be a binary relation between two things. OK? So off we go. So let's do this. It's going to be a very short relation because I only have two types. Right? So kind of giving the meaning here, right? These denotation brackets are saying, give me a type, and then I will give you a relation between two terms. This is a binary relation between two terms. Okay, and we're going to define it by induction on the type, because types are defined inductively, right? The syntax of types are defined inductively. Okay, so what is the relationship for Boolean type things? I'm going to write it this way, right? Binary relationships like equality. We write infix. I'm going to write them infix. I mean, you can model these as sets if you really want. They could be sets of pairs, and that notation can get very heavy. I'm just going to say M is related to M. How do I write it in the notes? Just so I do it the same. Yeah, M prime at type bool. This is a relationship when, so how is this defined? So these two terms are related at type bool when I run them and they both give me true or they both give me false. So this is M runs to true, as does M prime, or M runs to false, as does M prime. So they both run to true or false. Probably the most obvious thing, other than just saying true is related to true and false is related to false, I have to have the ability to run my program, so I add that in, right? This is kind of like Amal had, well, these two different relations, V and E, and part of that is due to the fact she was using a call by value calculus. I'm doing a call by name calculus, so things are ever so slightly different. So I'm doing things this way. What about function types? A arrow B. So when are two functions related? And it's going to be really similar to function extensionality, but kind of spelled out more explicitly. Give me any two related inputs, and I'll give you related outputs. Right? So functions are similar when they take similar ins to similar outs. That's kind of the motto. So that means these two functions are equal when I don't have to worry about like syntax and infinite premises, right? We're in the land of semantics. We can do crazy stuff like that. For all n similar to n prime at type A, the application of m to n is similar to the application of m prime to n prime at type B. Okay? That's the whole definition from types. I'm going to get a relationship, binary relationship between two terms. Okay? So that's the first ingredient. And what else is left? Does anyone remember when Amal was doing a proof? This is just, what does a type mean? But ultimately, I'm going to want to say something like, if two terms are syntactically equal using inference rules, then they're equal in that sense. So I need to say something about judgments, typing judgments. which means I need to say something about gammas. And what do we need to say about gammas? What did Amal say? She was doing unary things. So something like, if you give me substitutions for all the variables that are good in some sense, right? That's when so these gammas are describing substitutions, and the type assignments are telling us what goodness means for each input. But now we've got two things, so I'm going to have two substitutions. So I'm going to say two substitutions are similar when for every variable mentioned in gamma, those are similar according to the type that I assigned to them. All right, so there's going to be another one. There's more relationships here. So I'm going to say here in one shot, a little bit, when are two substitutions? What metavariable did Amal use for substitutions? Gamma? Yeah. I'll do the same thing. I think I used at sigma for S in the notes, but let's just do gamma here. So that's what you're familiar with. Doesn't really matter. It's just some thing that we're doing. So I'll write it this way. So when are they equal? Well, when for every type assignment, I am intentionally doing this different from Amal, in gamma. I think she did it inductively. Right, gamma could be empty. So I'm just going to say do the whole thing and then say for any type assignment that you can find in gamma, what should I know? Oh, and these should be different substitutions, of course. All right? Well, the x on the left, the thing I'm plugging in for x on the left should be similar to the thing I'm plugging in for x on the right when at A, because that's the type that I say it is. So that means that x, kind of write it this way to remind us that it's just the substitution thing. So this is a simultaneous substitution. So rather than one term for one variable, it's a bunch of terms being substituted for a bunch of variables. And you follow the same definition as before. So that has to be related to the other side, x at gamma, using type A, the relationship of type A. OK, so this is now, rather than turning types into relations between terms, this turns environments into relationships between substitutions. Yeah?
How do you read x blocks gamma?
So remember, for substitution, I wrote m, or I can even say x with n for x. So instead of a single n for x, gamma is a list of n for x's. Yeah. So just do them all at once, and then if you find in the list, you do a lookup. So it's called simultaneous substitution, so rather than one-off substitution. So what's missing? So substitutions go to, environments go to relationships between substitutions, and then I have to say something about my typing judgment. I'm going to use the same notation, so I'm going to say that the meaning of a typing judgment is what, right? So this final thing now is going to map a full typing judgment. I know she used like a slightly different turn style here. I'm going to try to keep the same notation. We're interpreting each of the fragments of our logic as something logical. So most things are relationships, but this is now just going to be a proposition, something which is either true or false because it's at the end of the day. And what does it mean? Well, for all substitutions, if I apply that substitution to m, oh, this should be not typing, but equality, right? So it's m equal to n. I could do typing as well, but let's do that. When are they equal? Well, when for all gamma related to gamma prime, then m, this is why I'm using that notation, if I perform a simultaneous substitution, which is just regular substitution, but a bunch of replacements all at once, then that needs to be related, the left-hand side to the right-hand side using that substitution, but the other one, at type A. So this is my entire logical relation, right? Turning types into term relations, environments into substitution relations, and then finally, judgments become propositions that are true or false. And of course, now what are we supposed to do as good citizens is prove the fundamental property of this logical relation, right? That's what we're supposed to do. What does that look like? So what is my fundamental property? Okay, what is my fundamental property? It looks like if m is equal to n is derivable, then the meaning of that judgment, m equal to n in A, is true, is derivable. So that's the shape pretty much every time. And then how do we prove it? By induction on that derivation, right? So someone has given me some big derivation, and then I have to do induction. I'm not going to go through that. As you know, that takes some time. I can present a couple of tips and tricks to make this a little bit more reasonable. The first thing is I'm going to say one more thing about my logical relation up here. So I've interpreted types, environments, and judgments. I can also interpret rules. And the nice thing about setting things up this way is it's a very generic interpretation. So all the inference rules have a form like this. So I have some hypotheses, right? These are judgments. So let H stand for judgments, and let J also stand for a judgment. So this is my rule R. I've got some rule R in my system. So what is the logical interpretation of this? Well, if the meaning of all of my hypotheses are true, those are propositions, then my conclusion must be true. So I can interpret this judgment semantically as saying if H1 and Hn are true, then the meaning of J is true. Okay? Does that make sense? I'm almost not really doing much. It's just like, yes, there are propositions. So I'm just saying if the things above the line are true, and I interpret them this way, the things below the line are true. Why am I doing this? Well, because this is the property that powers the induction. What do I mean? So the go by induction over this derivation. So I've got some long derivation, right? And then down here I have, it doesn't even matter. Let me not write it. I've got some J. It's a big tree, right? Syntactically, it's just a giant tree. If I know that every rule that I use to build that tree is true, then by induction, the conclusion must be true. How come? Well, at the axioms, I'll have some axiom rule that will have some intermediate conclusion with no assumptions, which just means it's true. And then I'll have some other rules, H1, H2, J prime, which at this point, right, the inductive hypothesis tells me that meaning of these are true, therefore the conclusion is true, and it goes all the way down here, right? So you can prove that any inference tree, any derivation built from true rules is true. And this helps you not get lost in the 100th case of this giant inductive proof, right? Because that's just doing the induction for you. Now we're focused on just saying, well, for each of the rules in my system, is its interpretation true? I don't have to worry about induction or anything. I can just say, let me interpret everything above the line logically. Does the thing below the line follow? Right? That's an independent thing, yeah.
How long do the premises for rules have an interpretation?
That's a good question. So the other one is, do all of the premises in our rules have an interpretation? And so let's go review them. And this is the second part of my tip and trick, is get rid of annoying rules. Syntactically. I mean, you can do it semantically, and it can be a pain. But what's the big one? So this is the big one, REFL. Right? So I would have to give an interpretation for that judgment, typing. And you can do it. Normally, that would mean a thing is typed A if it's equal to itself at type A. It could add that, or I'd have to interpret that judgment. So it'd be something like this. Let me just write it down. M has type A. The meaning of M has type A. I could define a separate unary logical relation, but let me just save effort. This says for all, well, actually, this is just the meaning of m is equal to m at type A. I'm being lazy here. Expand it into that where it's just the same m. Exact same thing, right? And I could do that, and then I'd prove a bunch more rules. Or I could kind of work syntactically and derive reflexivity from some other rules, which is what you'll actually see a lot in practice. And it's important because it's the same trick that lets me reduce compatibility to some easier to swallow bits, right? And what's the structure of that look like? So I don't want to erase that yet. Let me put it here. So to get rid of compatibility, I need a way to apply equalities in subterms. That's effectively what it's doing. Compatibility says I can equate subterms in a larger context. So a way to do that with some discipline in a small amount is every time I have a typing rule, double it up. What do I mean by that? Well, here's a rule. I'll start with the kind of axiom. X. So I had a rule for variables, right? So if I know x has type A in my context, then x has type A. So double it up. X is equal to x at type A. So this was my var rule before. Sometimes I do var squared, two variables. Right? And hopefully you believe that. Whatever you plug in, it's certainly equal to itself. That's like the basic case of reflexivity. What's another one? Let's do lambdas. So when is lambda x dot m having type A to B, right? So this was the intro rule. Okay. It's when we add x to our environment, and then we say that m has type B, and our x has type A. Double it up. So I have n equal to m up top, which means lambda x dot n is equal to lambda x dot m down below. So every typing rule, just you have two things, and now it's in terms of equality. How would elimination for functions go? Right. So if I have two equal functions at type A, and I have two equal functions at type A arrow B, two equal functions at type A, when I apply in whatever order, I get two equal outputs of type B. Right. And you just do this for all of them, right? All of them. The bool intros, true is equal to true, false is equal to false. The if then else is a mess, but you just do it. It's just two different ones, and the subterms are directly equal. And with these rules, you can delete REFL and turn that into just a bunch of the I squared and E squared rules. I guess also var squared. Same for compatibility. Whatever the context is, you can go by induction on the context. And most things won't change until you hit this spot, and then they're different. And so wherever that changes, you do that, and then you've got reflexivity. So we can delete these rules from our system entirely without losing expressivity, right, in a sense that anything I could have proven before, I can prove with a lot more effort using these more fine-grained rules, right? But that means I don't have to say anything about them because they're just shorthands for something that's easier to swallow. I can just prove, and this is where that notion, do I have it laid out nicely? Oh, no, it's up there. The meaning of a rule. So why is the variable rule sound? Why is its interpretation sound? I have nothing to start up with up here, but I say for any two substitutions, satisfying the relationship of gamma comma x of type A, what do I know? Well, I know x of type A is in here, so they're the same at type A, so they're the same at type A. All right, so this rule is sound, right? Its interpretation is true. And then you kind of go through, and most of this you're just kind of playing around with the meaning of substitution, right? What does it mean when I substitute across an application, or a lambda, or an if then else? So that's one thing we can do. There's one other step. There's kind of the trickiest part of this whole enterprise, which you can also deal with syntactically, which I sometimes find helps. And let's look at this rule, the stepping rule. I added a premise saying that the place I started from had type A. how come. If I didn't, I could have some random term which maybe wasn't well-typed, but then stepped to something that was well-typed. So this is necessary to make sure that in my conclusion, M has type A. My operational semantics in these relations don't care if the terms we're talking about are well-typed at all. That's not important. In fact, I think Amal probably said they have to be closed. I'm going to say they don't have to be closed. I don't care if the terms are closed. It doesn't matter. It's whatever you want. But what is the property that holds? So we'll have something like this. M goes to M prime. This is beta reduction. And M prime is equal to N prime at type A. And then N prime comes from N. Right, so this is a form of expansion. If I know that M prime is equal to N prime, and I can expand both sides to something else, then it must have been that M was originally equal to N all along at that type. And I'll call this expand. So this is a rule I could add to my system, but I lose the fact that if two terms are equal at a type, they have the type. But I don't care. It doesn't matter. It's not important for me, at least as far as the logical relation side is concerned. If I'm working syntactically, I might care. But once I get here, it doesn't matter anymore. And at the final point there, it won't matter. So I can prove that this rule is sound, right? And how do we do this? This is actually one of the most important properties of these logical relations. And you'll get stuck at exactly this point. And I'm sure Amal has mentioned it. She may not have written down this property explicitly, but she's used it when proving things, I'm sure, which is a closure under expansion. Right? And so it's just this idea, but said directly about the logical relations. So each one of these properties, so it's very obvious for the bool. And so let me write it down. So if M reduces to M prime, which is related to an N prime at A, which comes from an N, then M directly is related to A, or is directly related to N at A. This is expansion. So if I know two things are related, anything that reduces to those two things are also related. All right, so I can expand it out. Is that true of bool? Right, so this is something that's true of all the types. Is it true of bool? Right, so if two things are related, then I can reduce some more, and by transitivity, that's fine. So by definition, that's true. That's why I have the reduction there. Is it true of functions? So if these two things are related, if M and N are related, and I can expand them out, then I can still reduce on the two sides here, right, because they're in an evaluation context. So it holds there by induction. If B is closed under expansion, then so is A arrow B. So they all are. So that's kind of one important property. What's another important property of these types? You've heard of this partial equivalence relation. What's a partial equivalence relation? Anyone know? Yeah.
Not reflexive?
Yeah, an equivalence relation that's not necessarily reflexive, right? So this is, they are symmetric and transitive. And so this is another thing we can prove. So A, the meaning of every A is symmetric and transitive. And you would go through and prove this by induction, right? OK. But why do I say that? So if I've got this closure under expansion, I intentionally designed my logical relation to have this property. It's the most important property you ever want for a logical relation, no matter what you're doing. That means this expand rule, while it makes me sad that things aren't typed anymore, technically works. And why do I say that? I had those double up rules. You can actually delete some of them. So where did I put them down? I put them down maybe here, wherever they were. So I had some double upping rules, and you can delete some of them. So using expansion, oh no, here they are. I actually don't need that. That comes from expansion and the extensionality principle. So lambdas make sense because I can always expand them. Right? I can use the extensionality principle to apply them to 2 arbitrary arguments and then reduce them, and then that works. Right? I don't have to deal with lambdas anymore. That's a syntactic way of doing one of the main steps of a logical relations proof. Now I only have to justify rules like, what's the other one? I said out loud the one for functions that, let me delete the variable case. So m and m prime, if they're the same function, and if n and n prime are the same argument, then both applications are the same result. So m applied to n is equal to m prime applied to n prime at type B. So this is my doubled up elimination rule. So this is true, obviously, by definition, because of the way I defined it, right? So if I have this 2 functions related at type A arrow B, I have 2 related arguments, then by definition, their application is related. That's the definition. And then the extensionality rule goes the other way. It says if 2 functions are related at all arguments, then they are related. Right? So these 2 rules are just the 2 directions of this if and only if. Right? So these are kind of the tips and tricks that I will leave you with to actually proving these kinds of logical relations. You should go home and at least, or after hours, at least do one of them from Amal's or my lectures. And these are tricks that you can use either way. Like these are kind of universal principles. All right. Now I want to move on to the fun stuff, which is we're going to add polymorphism to our system. Right? We're going to add generic types. So hopefully everyone here by now is familiar with generic types. All cool languages have them, even imperative and object-oriented ones, so nobody has an excuse anymore. Right? We all know what generic types are. What do generic types give me? They let me say, you know, the type of the identity function is what? So the type of the identity function, you know, ID x equal to x is what? Right? We all know at this point, there's no principal choice other than saying it could be anything. Right? Any input, I give you back the same output. That's just what it is. Right? So this is alpha arrow alpha. So you do this in cool languages like Haskell and OCaml, and there's a little bit more syntax, but you do it in Rust and Java and C# and whatever you want these days. Right, it's a generic function, any type of input to the same type of output for your choice. And if we're going to be explicit about it, this is what I would say. For any choice of type alpha, it turns alphas into alphas, right? This is the kind of for all quantifier. Logically, this is a for all, meaning for all possible choices of types. There's another cool one, right, which has to do with modules in programming languages. So suppose I have something like an interface for a stack, right? So I have some signature of a stack where I have some abstract type, not a stack, a queue. Not that it matters too much. Right, so these are queues where I can enqueue and dequeue elements, right? So things can wait in line and then come out of line in a first in, first out manner. So I have enqueue. What is the type of enqueue and dequeue? So I don't know how my stacks are represented. That's abstract. You don't get to know. But you do know how these operations work. So if I add something to a stack, then you have to, and let's just suppose they're ints to keep things simple. So you have to give me the int that wants to wait in line, and you have to give me a current existing stack, and then I will give you an updated stack where that int is waiting in line. There's different ways to write it, but here's one. It's kind of purely functional without side effects. DQ says give me any stack represented as alpha. And, well, I'll try to take one out, but it might be empty, right? So I'll say something like maybe we'll get an int back, right? And then I guess I should give you an empty q, which is just whatever the representation of an empty q is some value of type alpha. So you don't know what these are specifically when you kind of abstract over this module. I may have implemented them as linked lists or a much more fancy structure that has better performance. You shouldn't depend on that, but you can use these operations. So how do we express this logically? Does anyone know? You may have heard of this one before as well. It's an exists, right? So this maps to something like there exists a type alpha such that I have three things. The first thing that I wrote was my enq function, which takes int arrow alpha arrow alpha. And what else? I've got some other stuff. I've got my dq function, which takes an alpha and maybe returns an int. So using something like Frank's notation, it would be like this, 1 plus alpha. So either I give you nothing because there's nothing there, I'll give you the alpha. And then if I have just the empty one, it's just a constant of type alpha, right? So for alls and exists, the plan for now is to talk about what are the rules for alls and exists, right? So we have a system that talks about this. So for all in particular is something called system F, or the polymorphic lambda calculus, right? System F is from Gerard, who is more interested in logical things, and this was from Reynolds, which was more from a program point of view. But this is a system where we have for all and arrow is system F, and we can also throw an exist too. That works pretty well, so you might as well do it. So I want to look at what does that look like, sort of what is the guts, and then how do we update our logical relation to handle it, right? So where are we going to put these things? I think I'll put one thing over here. Yeah. So let's start with our rules for how does it look. Actually, you know what? I'm going to erase contextual equivalence. And the idea is just as before, from the fundamental property, we can prove that if something is syntactically equal, it's contextually equivalent according to this definition. Actually, not too far off from what I did just with rewriting. Right? If they're syntactically equal, give me any context. By compatibility, they're still equal. By the fundamental property, I know their meaning is true. And at a Boolean type, it means they both reduce to true or false. Right? That's exactly what we needed.
As long as our programs are terminating, we can always keep equivalence, right?
Yes. So this happens to be a terminating language. So this only works for a terminating language, the way I defined it. If it's non-terminating, you'll have to do that kind of trick I did last time, where to handle the cases where I never actually evaluate. Like, if I evaluate and give an answer, then the other one does. Because everything's terminating, I wanted to save some time. Yeah. And in fact, not just save some time, this proves that they're terminating as well. Right? That's kind of the other thing, is we get the proof that it's terminating. If it doesn't work, if it's not terminating, this wouldn't work. Right? So that's kind of the nice thing. It's a little bit of a 2-for-1. All right. So what's the challenge for these polymorphism bits? All right, so I'm going to have my terms, m and n. I'll just list them out now. So I'll have all my lambda calculus stuff, but m applied to n. My lambdas, I will start adding type annotations. This is the way Gerard did it, so I'm going to do it that way. And how come? Well, we're also going to have, in addition to function application and function application abstraction will have type abstraction. So a term can abstract over a type variable, just like it abstracts over a term variable. I don't need to say what kind of thing, because it's only one kind, it's a type. And then what's the opposite of that is instantiation, right? If this is polymorphic over all choices of A, I can say I'm going to pick an A to instantiate that generic definition. So hopefully a lot of people here are familiar with this. They've seen this before. What about the existential side? That's a little different, right? Has anyone here seen the rules for existentials, at least the syntax? A little bit less common, yeah. So it's kind of the opposite. So for an existential, I have to say, essentially, if I implement, do I have it up there? Yeah, if I implement my stack, or queue, sorry, I keep saying stack, I have to actually say when I'm implementing it how I represent it. It is represented as a linked list, or maybe a pair of linked lists that I'm going to do the fun, efficient thing with, right? That I can choose different representations. Maybe an array that I'm going to cycle around. There's different operations, or different ways to do it. But I have to tell you, what type am I implementing this at? And then I implement these operations at that specific choice of type. That's the idea. So that means I'm going to have a package where I say, this is the type that I'm going to implement some code of a module for, right? And, well, yeah. And then on the other side, when I open it up, I'll have some sort of mechanism for opening up this package. And what does that look like? I'll just kind of write it like this. A case M of, and we're going to open up the package. So I have some abstract type alpha, and I have a variable with a type B that might refer to that alpha, right? I don't know what it is, but I have to refer to it for a while. And then I just continue on as something. So this is opening up a package, M, which has an abstract type and some implementation code that can refer to it for a while, right, while we compute some stuff. OK. So what are the typing rules? Let's add some typing rules over here. OK, the typing rules. So how do those look like? So my typing rules are going to be something like this. I have, I've got a gamma. And I want to give a type to, whoops. By the way, does anyone know what that big triangle symbol is? Capital lambda, just in case you're trying to write this in LaTeX. It's just a capital lambda. It kind of just looks like a triangle when I write it on the board. So when does a generic chunk of code have a generic sort of type? This is like the tricky one. This is what gets everything all started. So before, for lambdas, I had to carry around this environment to keep track of free variables, which stand for some sort of value. And now I'm going to have some code, M, and I added these type annotations because M might refer to this alpha in the type annotation of some bound variable. So I need to store this somewhere so I can refer to it later, right? So a typical thing is have another environment, theta for types. So if I want to check that a generic thing is well typed, then we add the generic type variable to our list of generic types, right, to kind of keep track of scope, and then just type check the body. And as far as making sure everything is sort of well formed, and the scoping rules, this M can refer to the variables listed in gamma. They might be free variables. It can also refer to the variables in this generic environment. So if it has typing annotations, it can refer to those. And the type at the end can refer to these free variables, right? And for it to make sense, these environments should close over those things on the right-hand side of the turnstile, meaning any free variables here should be listed in these two spots, and any free variables of the type should be listed there. Yeah.
I think I'm missing something.
Yeah.
Where are we guaranteeing that alpha's well type? Or maybe I'm misreading it.
So alpha stands for a type. There's only one kind of type.
Okay.
That's the trick. So if you go to much cooler systems like Haskell and presumably OCaml for a long time now, you'll have other kinds of types, and then you would need a kind annotation here. And the question is, how do we know that the alpha is well typed? But since I only have one type of thing, there's no real reason to do that. But I will allude to it in a second. So how do we instantiate? So this is the introduction rule for alls. What about using them? Presumably, I've got some generic code, which now looks like this. I've got some generic code M, which has type for all alpha.b. And I want to instantiate it. So what do I do? So normally, if this was a function application, I would say I have a well-typed argument at the type I'm expecting. Then I can apply them and plug it in. So I'll do something a little different. And this basically manages scope. I'm not going to write down all of these rules. Whoops. So this is my way of saying that A is a type. I'm using star for type, which is really common. It doesn't really matter. In the environment theta, meaning that essentially this judgment, theta entails a is a type, is the same thing, or will prove that the free variables of A are contained within theta. All right, so I only refer to things listed there. And you can list these out with inference rules, and I'm not going to bother, but just so you know that we're just checking that A makes sense in that typing context, that typing environment. OK, so if that all holds, then I can instantiate M at type A. And what is the instantiation? Is B, but I have to say what the generic alpha was. And what is the generic alpha? I'm instantiating it at A. So every time I refer to that alpha, I need to use A, right? I think that's what you're going to say. So this is the type B, where we now plug in the specific choice of A for the formerly generic alpha. This is instantiation, also known as for all elimination. OK. Now let's do the exists rules. So the package is the easiest one. So what does a package look like if? Well, I'll kind of do it a little bit backwards. So I want to type check that a package AM has the type there exists an alpha such that M implements B. And so what is A? Oh, I forgot my generic type variables. So A has to be a type that makes sense in this environment. I should check that. So A needs to only refer to the type variables I have in scope. What about M? What type of M should M be? M should be an implementation at B when we know that alpha is linked to A. Right? So it's the same substitution. B, where I plug in A for alpha. So internally, I know that alpha is A, but externally, I do not. That's the idea. It flips the genericness. Last is the unpacking part. So if I have, I keep forgetting my type variables, if I have an existential package and I want to use it, all right? So intuitively up top, if I know that M implements B for an unknown choice of A, how do I use it? Well, I could have some code that doesn't assume anything about alpha and uses, right? Oh, that's the other link. Right, the other link I forgot, I'll write it here, is that gamma might also refer to those free type variables. Right, so the type of the free variable x might refer to this alpha that we're introducing locally. And I don't know what it is. It has to be totally generic. Then I produce some output, C. OK. Then I have a case statement. So this is the case M of alpha x of type B gives n, and this has type C. Is everyone happy? There's one little wrinkle here. Can anyone spot a scoping issue or a potential scoping issue?
C shouldn't refer to alpha, right?
Yeah, I mean, C can refer to everything in theta here. That's fine. But technically, C up here might refer to this alpha. So you have to rule that out explicitly. Sometimes you write this as a explicit caveat that alpha is not in the free variables of C. And if you were actually implementing this, you would have to check it or you'd conclude bogus things. This is annoying when you're implementing type checkers. That's something to mention. OK, so these are the typing rules. The last thing to make this a real language is the operational semantics, right? So what does that look like? And so the operational semantics, well, I mean, honestly, you can just predict them. This is like a function. This is like a pair. They behave like pairs and functions, right? The fact that the rules are unsurprising is maybe the surprising thing, that we actually don't do anything interesting. So what do I mean? Well, the beta rule for all is what? If I have a generic chunk of code and an instantiation, how do we reduce? Well, we just update all of our typing annotations, right? And then if I have a package, this is the other beta rule for exists. Forgot to backwards my E. If I have a package, and then I open it up, alpha x of type B, then we just plug everything in, right, point-wise. B, so this is going to be n, where I plug in what? I plug in A for alpha, and I plug in M for x. And one thing to note here is I don't actually care what this type annotation is. It's only for the type checker. The runtime system ignores them. Right, that's something to keep in mind. Same thing for, and you saw that in other people's presentations, the type annotations here have no impact. I'm not like actually checking that my argument has type A in any meaningful sense at runtime. We just do it. OK, so this is the operational semantics. Now I want to go update my logical relation with some more stuff. And I'm going to need more space. So let me put it perhaps down here. All right. And we're going to have some problems off the bat that we're going to have to address. And so what's the thing? So my syntax of types include what now? So I've explicitly mentioned A and B could be functions, certainly. A for all, B. And we saw this before. It exists, alpha.b. How do I use alpha? Yeah, I need to add that, right? So that's another one of my types. This is annoyance number one. So I'm updating my logical relation. So I have to say, what is the meaning of alpha? What's the meaning of alpha? Could be whatever, right? So we do the usual trick. We have an environment that we're going to thread through that just tells me, right? So I'm going to have some extra little parameter tau. Let me make this a little bit nicer. So tau is going to tell me whenever I hit a type variable, what is the meaning, right? It's just like we map variables to values. Now I'm going to map type variables to the meanings of types, which are relations. So this is just look it up. So if M is related to M prime at that case, okay? So this is the first problem, and then the annoyance is, okay, now that means taus go everywhere, and then we update the definition, and it's a big pain, and then I need one here, and I'm just going to do this pain real fast now. We have to thread everything through. And then until we get to the top, right? what do I mean there? So my judgments now have these free type variables, theta. Okay. So I'm going to have to spell out for all tau in the meaning of theta, which is going to be a whole bunch of substitutions, and I'll spell out what that means in a second, and then we can introduce it here and here, right? So this theta tells me how I'm going to interpret these types tau. And I know I haven't said what that is yet, so just let's hit a pause, but that's what I need to use that information for. Okay, so that's problem number one. Problem number two, for some of you might be obvious, but let's just start doing it. Now I need to interpret the meaning of for all, alpha.b. Okay, and how are we going to do this? So I have m is related to m prime at the alpha.b. And what's the, are we done? Oh, we started really late. I guess I can just finish now. We started at like the hour. We can stop now. Do we want to stop or keep going? Okay, I'll just finish this definition. Yeah. Where was, okay, so, right, so let's keep going. What is the obvious interpretation here? Well, for all types, it works, right? So I'd say something like this, for all types A. Okay, then what do? Then M applied to A has to be related to this. So we're going to plug in the meaning of A for tau. So this kind of looks like this. Translate A, plug it in for tau, M prime applied to A. So what I'm saying is pick any type you want in my language, translate it and figure out what logical relation that should have. Plug it in for, oh, I should have said like this. Plug it in for alpha. Leave the rest of tau alone. So we're updating tau. All right? Does this make sense? So Amal was talking about recursive types. This is like even worse than the recursive type problem. I'm saying take all of the types in my language, including this one, has to be defined before it's defined. This is a problem, right? So you could solve it, I guess, using steps indexing, but then that's sad because you miss one of the really fun and exciting results, which is like this. Okay, so how do I fix this? Well, I'll have another parameter. I have to update everything. And what is this? These are the candidates. I'm going to tell you in advance what I'm going to turn all of my types into. These are what the interpretations of types as relations is going to look like. This is part one. And so what do? We say for all A in type, and I'm going to say semantic A in C. So this is a syntactic type. This is a binary term relation. And now I'm going to say, instead of translating A, which I don't know how to do that yet, I'll just trust you. So this is blind trust, essentially, on the part of B. And, well, the first thing, what is the relationship between the syntactic type A and the semantic type A? Is there one? I just picked two things. So it's totally arbitrary, right? So these are completely arbitrary things. In fact, I could say, let A and A prime be two arbitrary types, and let this be an arbitrary relationship. And off we go. So I'm just lying to you. So I've got something like the polymorphic identity function. And I'm saying, well, tell me what type you're going to use, and then actually use me at a different type, and it'll all be fine. Right? This is like the biggest trick. The fact that this works is the biggest trick that makes impredicativity, if you've heard this word, and system F and polymorphism, it's exciting. It's the fact that we can get away with this lie. Because the the type annotations are totally useless. We don't actually use them for anything. I will do the same thing no matter what you claim, which type you claim to use me at. So the situation is something like this. If we have the set of all binary term relations, and then we'll have kind of specific interpretations of type here, like bool and type A arrow B, among all of the term relations. Some of them are closed under expansion, and some of them are also partial equivalence relations. And the ones that I know about are definitely both of these, right? So I can label these two sets. These are relation candidates. These are all the things that are closed under expansion. These are equivalence candidates. Not only are they closed under expansion, they're also symmetric and transitive, right? And so we can say this notion of a relationship that's closed under expansion and symmetric and transitive exists before I start defining any of these logical relations. And so therefore, I get to thread that through and say, OK, I can interpret this for all relation candidates or for all equivalence candidates, and then push the proof through, right? And then we can prove soundness just like before, and it all kind of works. And then the power is, yes, my actual language is there, but I can have other weird types that I don't have any syntax in my language to refer to, but I technically can plug it in and then prove interesting new properties without having to add anything new in my language. And that's where the power of free theorems is. And we clearly don't have any time to talk about free theorems, but I kind of wanted to discuss how we do that, how we push everything through. And you can prove soundness for both for all and exists. What is the thing for exists? It's the same idea, but they both have to simplify to some package, right? So this means that both M reduces to a package A n, and then M prime reduces to a package some other type and some other term. And they're probably represented different, actually. But there exists a relationship where they're symmetric, or where they're not symmetric, but where they're related, right? So then there exists some meaning A in C such that n is related to n prime at B, where we substitute the meaning of A for alpha. Right? So that's the existential. All right, so I'll wrap up there so we can go to lunch. I think that's about the time since we started from about the hour. And then we'll talk about a different topic tomorrow.